Hello, Sotiris. Ah, you are mute.
As always, hi everyone. Finally, we didn't let the
How are
song
you?
play entirely, did we?
You did what did you say about the music?
Yeah, we didn't let the whole song.
Really?
I don't know. I don't know. I just heard up to the up to a point. I'm not sure.
Okay, how are you? What time is in
Okay.
Greece?
Okay. Right now it's 5 p.m. Here. You are aware.
Yeah, today first webinar from the United States in San Francisco, 7 a.m. in the morning. Yeah, different timing.
Which is
So
much harder
yeah,
than
yeah. From now on, next 3 months, all webinars with me are going to be from San Francisco. Um, this is the normal timing for more European contacts on people that normally follow us every week, but we'll have more webinars for the US timing maybe next week, so stay tuned. Well, so what do we have for today, Sotiris? Because do I after breed? Um, this is not a normal topology. Maybe it's a little bit more advanced. So what you can tell me about it?
Yeah, so we have explored some other usual ones, like in the previous webinars. This is the first one that has a feature that the other ones didn't, which is bidirectional power. Power can go from the input to the output and the other way around. Where is this useful? This is useful in the EV market, especially when they're thinking about your house powering up the car, but then the car powering up, stabilizing the grid. This is the concept, one of the concepts where this is usual. This is like, I think it's not the easiest one to work with, but well, it can get complicated, even this one, but it's one of the first topologies if you want to learn about bidirectional power that you will encounter. So I think it's a good topic to start with.
Uh, what are the industries that use more, or maybe can you put
Well,
an example to understand better?
um, mainly the ones that I have seen, I don't know about. They're exotic. They're always exotic, applications. But the ones I have seen is like the end load is maybe well, it's a battery on the one end, and in the other end, it's a grid, not a charger. The charger
Okay.
is our topology mainly, but it can act as a UPS system as well. You have a battery, and then you have a power outage, and power comes back live. So the UPS systems as well. The EV application in this sense with your house and your car, but there are other topologies there as well. But that's the concept is backup. You have a main flow of power to your load, essentially. That might be a battery or another configuration, and then you need at some point to reverse the power flow.
Good.
Yeah.
So a lot of details to take into account.
It's not like a simple one. Like I cannot think of an appliance that uses that, like where like the flybacks, for example, your phone charger uses it. I mean, that's a very simple one to explain, but this one, no. Yeah, okay, let's start the presentation. Sorry for being that abrupt here, but I guess I can share my screen. So let's go in for the topic. This is the very basic schematic of a dual active bridge that people should be familiar with. I mean, we do have two full bridges in this topology, and we connect those two bridges with a transformer and maybe an inductor in series. And that's pretty much it. Now, the things that I want you to remember from these slides is that we have those, I call it leg AB and leg CD on those two bridges. Power can flow from this direction, from the input. That's the standard one here, like the input to the output. So this is the leading bridge, and this is the lagging bridge. That's the naming convention to remember. And we can go the other way around, right? So this is leading the power, and this is lagging. Now, C1 and C2. Those are the control units. I will write those you will see C1 and C2 in the next slide. So just remember that this is the control unit of the input side, and C2 is of the output side. If we follow, this power direction. All right. So yeah, let's see a little bit about the control methods. Now, the ones I know, because there may be others, are single phase shift, dual phase shift, and triple phase shift. Those control methods are about the phase shifts that can be controlled. So the single phase shift controls one phase shift. The dual phase shift controls two, and the triple phase shift controls all phase shifts possible. Which are these ones? These are the very basic one, the phase difference between C1 and C2. That's the first one. Then there is the phase difference of C1 between leg AB and CD. If we go back, those can have a phase difference, like a phase shifted full bridge, for example. And that can have also a different phase. So we have this phase between these two, that phase between these two, and then we have C1 phase and C2 phase. I mean, the delta phi between those two. So we have essentially three phases. Now, in the single phase shift, we control the C1, C2 phase difference, and we keep the internal phases, let's call them like this, it's easier, to 180 degrees fixed. In the dual phase shift, we can vary that internal phase shift to a different number than 180, but it has to be the same between the two bridges. So we have 2 degrees of freedom here. And in the third case, as you understand, we can play with all the variables. Now, the SPS is the control method that we're going to see today. All right, again, controlling C1, C2 and keeping the internal phases locked to 180 degrees. First things first, pros of this control method is that it can actually achieve zero voltage switching for all FETs under certain conditions, and this is today's topic. Actually, one of the main topics is to see the zero voltage switching. One other thing is that it's simple to implement because, as you know, actually that's the simplest one to implement, 1 degree and 1 phase to control. So that's that. We have high efficiency under heavy loads, and we have acceptable current stresses on the switches. What do I mean here is think about, yes, we are in a ZVS condition. Assume that we are in a ZVS condition, right? And then there is the conduction losses. Those conduction losses have to do with the reactive currents inside the bridges, and there is theory and the theory compares. I mean, each case there are different other control methods that are not that good. Other ones are even better. I think they're somehow better than this. This is acceptable, okay, and we will see how. What to choose to get this to a low voltage point, but because the point is, it's not like zero voltage switching and then game over. No, you have to control actually those reactive currents inside in each bridge to make sure that they're not excessive and causing extra thermal losses. without producing any power at the output, actually. That's the thing. Now, the cons is that we have turn-off losses. We can't get away from that. But, gate driving, if you play with gate driving and have a fast turn-off, you can pretty much minimize those ones. Let's see 3 things here. Now, take a look at the clouds about these ones. The first one is about D capital, and D capital is pretty much like think of it like a duty cycle parameter. That's the only variable that we are going to control in the SPS method. If you vary from a D from 0 to +1, you will have the maximum. You can actually not the maximum, but the power flows from the input to the output. If you vary D from 0 to -1, that's a negative phase shift actually, you reverse the power. And okay, so we have this capital D notion of, think of it like a duty cycle for now. Now there is the D, the small letter D, which I think of it like the voltage in-out ratio. It's not the turns ratio, it's a ratio between the input voltage and the output voltage. So if we have a 400 volts input voltage and a 40 volts output, for example, and you have a 10-to-1 turns ratio, exactly if you choose 400 volts and 10 and 40 volts at the output, this D will equal to 1. This is essentially, what you have designed it for. Now, if the output starts deviating or the input starts deviating, then D is not going to be equal to 1. And this is a good idea to keep in mind that we choose this value to be close to 1, and there is a reason why. Now, the star of this topology, I would say, it's the leakage inductance, because this actually controls the maximum possible power transfer in the bridge. Now, if you select a D max and a P max, you'll find the leakage that you need to actually deliver that power. All right. Now, what about the ZVS areas? All right. What you see here is a graph. Give me 1 moment to switch pens here. To switch my pen. Sorry about that. All right. So, as you can see, we have a no ZVS zone here and another one here. And if we play in this area, yes, we do have ZVS. Now, this is not this is a really nice graph, but it shows half of the truth, pretty much. Okay, I'll explain later why. Now, what is this? This is the D that we said that we want to phase. Basically, as D comes close to 1, we have to 0.5 actually. dP is a better number. Like, let's play with degrees. If dP is 90, we have full power. That's not a good point to operate, though, because of reactive currents. So we will see that we will choose D around 0.35. So phases up to 65 degrees is a good compromise for this. So we will choose our converter to operate to a maximum dP of 63 degrees. Okay, let's put it into degrees. Now, these two, I can say, green lines, this first one explains this term, right? And the other one on the bottom explains that straight line. But those are necessary conditions, but are not enough. because we have to take into account the leakage inductance and the actual equivalent capacitances of the input and output bridge. Now, if you put those that term and that term into the game and plot again for D, you will have something like this. Something smaller than that, because this term has something inside. And effectively, you need to operate above a certain point. Now, if you fall below that number, you would have essentially it will be a non-CVS area. So that's a better graph to plot. But again, we cannot do that here because we need to be exact with numbers. But in reality, this area here is going to have the ZVS 100%. This is the necessary conditions and enough. Necessary and enough conditions. I think that's the wording in English. Okay, so the equivalent capacitance is what do we have in this term? The leakage, you understand what this is. The equivalent is, if you take one of the two bridges, for example, like A, B, or CD, I guess you are having the same MOSFETs. If you add the COSSs of the MOSFETs and you add actually the input capacitance of the primary or the secondary one, it depends on if we look from the input or the output side, that's the equivalent capacitance of the bridge, of the leading or the lagging bridge, depending. So you have those two parameters as well to calculate here. Now let's see if we have any question, because yep, I want to discard. See if we have any questions on that. Sorry about this. Okay, how to measure the transformer capacitance? That's a good question. Essentially, it's about the open load capacitance of the primary or the secondary, and you can measure that. Well, the best way I can think of to measure it would be to take a body plot, essentially to get the self-resonant frequency to find the effective capacitance in the input. It might be more straightforward than that, but I guess a self-resonant frequency plot is going to tell you the truth. You know the leakage inductance already. Yeah, actually, if you have an open circuit, if you have the secondary open and you measure the primary, you have the magnetizing inductance there dominating everything. And if you take the resonance plot, you can see in the frequency that it's interesting. It's not going to play a huge role, but you'll have essentially solved the equation for C, and you'll find that from the graph. To schedule a switch to go from double and triple phase shift. Okay. Me personally, I've dealt with the first topology. The DPS and the triple phase shift are more complex. If there is enough interest, I guess we can schedule something, but that's not it. There has to be some request for that, because the material is not ready for this. Let me go back again. So can we start sharing again? See. All right. Perfect. Now let's go here again. We have covered this, and we are, whoops, I'll step back. We're in this point now. Okay, now zero voltage switching equations. The workflow looks like this, at least the one I follow. You first select, you have to find the leakage inductance. I mean, you know the maximum power that you want to transfer, right? You know the input, you know the output. The turns ratio, it's something that I'm gonna put a question in the next slide for you to find out. And okay, let's say that this is an easy one to figure out. And basically, you need to calculate the leakage, but Dmax, how should you select, a Dmax? Basically, my comment about reactive currents was exactly this. If you limit Dmax to 0.35 or dP to 65 degrees, as I showed you in the later graph, you will limit the reactive currents to a good point. Above this number, you can play, but you're paying a price. All right. Now, these two equations are exactly the ones that we saw here, right? These two, except that I wrote here, like this is the D capital to achieve ZVS, and basically you need to satisfy both of these equations. So there will be a minimum D capital that achieves ZVS, and there will be a maximum D that will deliver the power, the full power. And okay, for if we know the DCVS, then we can find the power for this capital D parameter. Now let's see a design example, because it's there are a lot of equations, but let's make it a little bit more clear. A 1.5 kilowatt dielectric bridge. All right. 400 volts in the input, a 48 volt pack, a battery pack, a 200 kilohertz, and the equivalent input and output capacitances. You see them on the table. Now, the magnetizing inductance is not critical, by the way, at least for this topology. I think it goes the same way for the other ones as well, but at least for one, it's not critical. If somebody disagrees, you can feel free to correct me in the comments. But I haven't seen any relationship, at least with something important. As far as ZVS is concerned, in these types of things, there is no connection. But it might be another parameter that I'm missing right now. So leakage, turns ratio, and the zero voltage switching points. Starting off with the N, because if you remember, to calculate the leakage, we need the N parameter to decide about the N. I'm interested if any of you has any idea about the N. I'm just gonna take a sneak peek right now to see if somebody has an idea. We can wait a minute. Can you think of a reason to choose N to a certain number? The silence is deafening, so I'll step back and say exactly what I have in my mind. Let's see.
Sotiris, we have some replies in the chat.
We do? How?
Yeah.
I was just checking.
In the chat.
Not the Q&A.
Yeah.
In the chat. All right, I missed that. Try to keep D equal to 1. Exactly. D may try to accommodate D equal to 1. Choose N to have D equal to 1. Should N be placed in the range of 0.1 to 0.15? Yes. All right. D equals to 1, and the last reply is 400 volts and 47 volts. D equal to 1, yes, but not at 47 volts. I want to get it at 54 volts. And why? Because I have two operating conditions in mind. Let's assume these are the only ones, right? Charging at full load from 400 volts. Imagine the battery is discharged, right? So we're at 47 volts. We're charging at full power. Then the voltage starts building up on the battery, right? And we end up in 54 volts. Then we are charging with a partial load to maintain ZVS. That's what I had in mind. And then we can stop the switching for after a few, in a certain amount of time. So that's the scenario here. But N, should I choose? Okay, D equal to 1. You got that right. But N has another thing going on. So D equal to 1, okay. So N will be simply, if you take this equation, it's straightforward, but the output, what should be the output? 4754 volts. It should be the high voltage case. Why? For the reason that we want at 54 volts, it will be a partial load, like a low load condition. So we are approaching, the zero voltage switching, limits. So remember before, how can I do it again? It doesn't let me do it now. I'm not sure why. I had the pen here. In any case, I had the pen, but I can show you like this. We're going to play like this. If you put, the leakage number and everything, you'll have something like that. And this is the low power output. You will play, imagine you'll play from 20, 30 degrees, like the lowest power, to achieve ZVS, and then you can go higher. And of course, at full load, you're gonna have ZVS. But the worst condition is approaching, a few degrees, so low power. Power goes delta P, is essentially completely analogous to the power output. Like from 0 degrees, no power transfer, 90 degrees, full power transfer. So you can think of it as this is the power axis on the bottom here. So if we are close to 1, D equals to 1 in this case, then we're in a good place. If D equals to 0.8, we will land down here, for example, which is bad because there goes our ZVS point. So I'll try to keep D equal to 1 in this 54 volts low power output condition. All right, we are in this slide. Now let's put it into full mode. All right. So at 54 volts, it's 7.4, the turns ratio. Now the max, we said we're going to limit it to 0.3, 0.35. The lowest you go, the better. Essentially, how low should you go? It depends. Like if you limit this number a lot, you're not gonna be able to deliver power. So you're gonna have to make the transformer worse. Essentially, yeah, there will be drawbacks, or you may not have enough range to play. Like if the D value plays from 40 to 50 degrees, you just have 10 degrees So you can have a lot of problems in the converters, but this is like a sweet spot, 50, 60 degrees. We're calculating now the leakage, and we have everything to calculate as well, the powers. So at the DZVS is at 22 degrees, and we have 890 watts above this number, we have ZVS. Below this number, no ZVS. And the maximum that we can deliver, okay, is above the 1.5 kilowatts, so we're good. And this is what I say here, from 22 to 53, this is our two operating points. Like OP1 is going to play at not 53, something below that, and OP2 is going to play around 22 degrees. Still having ZVS for every MOSFET, okay, in this case. I think that's it for the presentation. We have here the references for you to take a look. Exceptional work from especially the first application. If you take a close read at this one, you'll see more details about dual phase shift as well. Sorry, dual phase DSP. And but the problem is that these references use the same letter for different things. So be careful. D capital here might be D small there. I didn't do it on purpose, but the different ones had, is a thing that happened. Same letters for different things. So let's go into Frenetic Online. Unless there is a question, let's quickly check if there is a question.
Sotiris, I'm here again. Not sure if we are running out of time.
We are running
not
out
sure.
of time. That's what I saw.
Yeah. A lot of people is asking about if we can share with all attendees your presentation. So your slides, I think there is no problem to share with the recording this week. So we'll send the common email with all the material. Okay.
And I think, since I guess we're running out of time, we can see the Llkg bridge, a design actually in Frenetic Online next week, like a short one, or do you want to continue?
Yeah, maybe you can quickly have a look to the Frenetic simulator, and maybe next week we can continue with the part 2 and how to design in Frenetic magnetic simulator this dual active bridge. I think would be interesting.
So let's keep it for next week. Let's keep what we have until today for next week. Because we need a little bit of time to explain there as well. I didn't have a clue. We ran so much out of time. But I think sharing the slides today will make sense because people are going to be able to follow better next time that we're going to see the transformer. Maybe I'll have another go, another idea, a more interesting example than this one. But I guess that's a good idea.
So let's keep the practical session for next week. I think it's gonna be better for everybody. So you can focus only on the tool.
All right, perfect.
Okay.
We have a user that wrote something. A lot of people in the call yet. So the magnetizing LM directly determines the magnetizing current. If LM is too low, the magnetizing current becomes excessive, which increases winding losses. A rule of thumb, the magnetizing current should be kept low, about 5% of the rated current. Based on this guideline, you can calculate the minimum LF value that should not be compromised. I think Ian is very right. And I probably know which Ian he is. It really awfully resembles the LLC well, the LLC is more tricky because you play with a magnetizing and to leakage ratio there, but essentially, yeah, that idea still holds true. So, yeah, I'm gonna take it into account as well. I'll check my design for this as well. Pretty sure every design that you see has a magnetizing inductance. The dual active is around 1 millihenry, 2 millihenries, which are big values. I mean, for safety, because if you decrease the magnetizing inductance to something like 100 microhenries, then yeah, you can have excessive currents there, magnetizing currents, which don't make sense. All right.
Right. So I think that's the last comment. So okay, we can end the webinar for today, I think.
Okay.
Thank you, Sotiris, for the webinar today, and thank you everybody for joining. Next week or next sessions, we are gonna continue with the practical session with Sotiris and with the tool. So we put in practice the dual active grid design. Thank you, everybody. Bye-bye.
Have a good one, everyone. Bye.